very much. I've been enjoying this conference a lot, and it's a pleasure to be here. So today I want to tell you about a long-term joint project with James Teller, which started a bit less than 10 years ago, and we've been working on that stuff, and I don't know, it might take some number of years more in order to complete, but we're at a stage where we have a fairly clear vision of what we're doing. It's about chiral CFT. The first thing I want to do is spend a couple of minutes emphasizing or spelling out the chiral CFT versus full CFT. These are two physically different concepts. They're just two different things. And I also very much take the point of view that each one of them is a thing that is a standalone notion. A chiral CFT is not the chiral half of a full CFT. A chiral CFT doesn't need a full CFT in order to exist. Just like a group is not the group of symmetries of some vector space. A group is just a thing on its own. So there are relations between these two notions, but they're both two standalone notions. And we'll start by quickly saying things about full CFTs that presumably you're familiar with. So this is a particular class of two-dimensional quantum field theories that exhibit scale invariance. They're defined on all Riemann surfaces. There's a notion of local operator. Some people call them local fields. I've been told that the more like the physicists like the term local operator better. And if you have a Riemann surface, sigma, and you pick a number of points on sigma, and at each point you select a local operator, so phi I is the operator that goes at the point zi, then there's this thing called the correlator. This is the schematic approach. In order to make this actually concrete, precise, you need to specify a couple of extra pieces of data. Around each one of these points, you need to pick little coordinates. That's one thing that you need to do. And the other thing is that you need to pick a Riemannian metric within the conformal class for sigma. Once you've made those two choices, then you get an actual number. And if you change these choices, for example, if I change the little coordinates by a rescaling, there's a factor, factor that comes out in front. So it's like the transformation laws are explicit for these kinds of things. So chiral CFT, in contrast, is not a standalone 2D quantum field theory. It is a boundary theory of a 3D TQFT, 3D topological quantum field theory. And what this means is that in order to have well-defined correlators, you need your Riemann surface to be the boundary of a three-dimensional manifold. Now, if your Riemann surface happens to be the sphere, you don't need to look very far to find a suitable three-manifold. You can you have a three-ball that does it. So when you're doing genus zero stuff, you might not notice this need for this three-manifold. But definitely if you do higher genus, if I have a torus, there's no canonical three-manifold that fills a torus. If you change the x and the y coordinates on the torus, what is the interior and what is the outside of the torus will flip. Another important feature is that local operators now are charged or can be charged. And they live at the end of things called Wilson lines. These are these lines that are drawn in orange here. These are lines in the bulk, in the three-dimensional bulk. And these converge. So you can, here I put a trivalent point in the bulk, which is, so there's this notion of fusion of Wilson lines, which I denoted by this symbol. So fusion lines can fuse. The coupon is labeled by a morphism of Wilson lines, in this case from I fuse J into K. And so once you have one of these configurations, when you have a Riemann surface, a three-manifold, the points, each one has Wilson lines. These Wilson lines go and do something. They could create a knot inside the three-manifold if you wanted. Then you have the correlators. This is all subject to the same caveats that exist over there. You need to have little local coordinates, and you need to have a metric on the Riemann surface in order for things to be well defined. Otherwise, it's only up to a scalar. If you restrict to the subclass of local operators that are uncharged, so there's all the local operators, and there's the ones that happen to be uncharged, so they don't have any Wilson lines that come out of them. And if you restrict to genus 0, then these two pictures start to look very similar, because you just have the sphere, and you have points on the sphere, and so for those who restrict to this special case, then there can be sometimes a confusion about what is what. Yes?
So did you specify what charges are and what the funny tensor there is?
This is the general setup. I'm not specifying anything. I'm just telling you this is the structure that exists. I didn't tell you how to get that. So my goal is to, long-term goal is to construct examples of these guys in a particular axiomatic setup known as the functorial approach to conformal field theory, which was pioneered by Graham Siegel in the late 80s. So he did it for the concept of full CFT, and he had some kind of ideas of what to do for chiral CFT. He used the term weak CFT to do that, but it was, whereas for this, Graham Siegel had something that very much counts as a complete definition. For that, he had some ideas, but I think they're sort of like extra. To me, it counts more like a sketch of how to make things in that context. So
the idea is that once you have these, you can put together two copies and get the full CFT, or so why do you want to do the chiral thing?
Because I prefer chiral to full. I'm that kind of person. There are relations between chiral and full CFTs. I suspect that there exists, in particular, a way, given a full CFT, to extract two chiral CFTs. One is the chiral part, one is the anti-chiral part. I also suspect that, given a chiral theory, chiral CFT, there exists a canonical way to construct a full CFT, known as the diagonal full CFT associated to the chiral CFT. So these are the ways in which these two concepts talk to each other. But it's not like, I'm not motivated more by this and doing this because of that. I happen to be motivated more by that and have a side interest in this because lots of people do that. But that's, from a representation theoretic point of view, this is the thing that comes first. From the path integral point of view, or from the lattice model point of view, this is the thing that comes first. Okay, so it's a matter of how you approach the theory. Okay, so now a little bit about the history. All the various axiomatic approaches to conformal field theory that exist, the functorial approach is the least developed of all of them. So there's this initial paper in the 80s by Graham Siegel. That's actually a paper that Graham Siegel would describe himself as being an unfinished project, because he did not manage to construct the chiral WCW models that he so much wanted to construct. Until 5 years ago, the only examples of CFTs that were constructed in that framework were the free theories, free boson and free fermion, nothing else. There's a complete absence of any kind of general structure, like papers developing the general structure of like things that say, if I have this, then these properties, like, and then roughly 5 years ago, there was some sort of major breakthrough in the area due to the work of Guillermo Pupiar and Hausdorff Vargas, where they constructed Liouville theory in the functorial approach. So this is for full CFT. And then another one compactified the imaginary Liouville theory, again, in this approach. Okay, so let me tell you a bit about the functorial approach to quantum field theory, and I'll first do it for full CFTs because it's going to be a bit more familiar to some people, and then I'll tell you how it becomes. So there's sort of two variants. Okay, so full CFT, so this is Graham's idea, is functor from a thing called the complex formalism category to
André?
yes.
Just quickly, the VOA approach, so
VOA is chiral CFT.
But then in this list, there is no chiral CFT constructed by VOA.
Sorry?
In this list, there is no VOA construction of anything. You said chiral.
No. If you want to, well, first of all, I didn't tell you what the functorial approach to chiral CFT is. I'm about to tell you that. It's a thing that.
Okay, no.
Then,
Okay.
so if you want to establish the full axioms of a functorial chiral CFT, that's a goal that some of us have, a common goal. I think Guy Huang is also very much motivated by that, and it's not a goal that has been achieved yet.
So the message is that the VOA or CFT VOA does not give you a functorial approach.
Well, it should, but if you start from a VOA and then you have first of all, the stuff that I have up there is not an axiomatic setup. This is just some stuff. I didn't list any axioms. This is just some stuff that you get if you have a chiral CFT. This is not a definition of a chiral CFT, because I would need to say, for example, how the surfaces of different genera like talk to each other, which is not talked about. So, yeah. So if you want all these, so let me tell you what this is and then what that is. And then. So from complex formalisms to Hilbert spaces. So this is the main idea. There's a sort of thing called the complex formalism category, and there's a thing called the category of Hilbert spaces, and it's a functor. So now let me spell it out for you in ways that are a little bit more down to earth. So first of all, what is this complex formalism category? It's a thing that has circles. To each circle you have a Hilbert space, and that has these two manifolds that have a bunch of circles on one side, a bunch of circles on the other side, and a two manifold in between them. That two manifold has a complex structure, and to those you assign a map between Hilbert spaces. So the circle has a Hilbert space. So first of all, we have concretely, S1 maps to a thing that I'm going to call H, that's the Hilbert space of the theory. And then, if I have a complex cobordism, so that's, well, it's a two-dimensional manifold. There is a complex structure. It's a Riemann surface with boundary. So there's complex structure here. It's important to distinguish the two boundaries, and one of them is called, let's call this one the incoming boundary, and let's call that one the outgoing boundary. Each one of these boundaries is identified with, is parametrized by a bunch of circles. So here we have a union of n circles, and over there on the other side we have a union of, let's say, M circles. And there's a chosen diffeomorphism between this and this boundary and this and that boundary. And then, given that, what you're supposed to get is a bounded linear map between the tensor power of n of h, or the number of incoming, to the tensor power of h for the number of outgoing components. And this should be is subject to a number of axioms, and the axioms is, well, continuous dependence on parameters, compatibility with composition, compatibility with disjoint union. If I take one of these pictures, another picture, then I have the disjoint union of two things. The associated map should be the tensor product on the other side. Compatibility with permutation of the components. If I permute the ordering in which these things are, then I get the corresponding permutation there. And because I care about unitary theories, I also want compatibility with adjoints. If I exchange incoming and outgoing, replace the complex structure by its opposite complex structure, then I want the corresponding map that I get here to be the adjoint of the bounded linear map. Yes.
Did you say the circles come with the parameterization, or rather the way that the surface in between?
There's a chosen parameterization of this incoming boundary by this particular explicit manifold.
And there was an axiom saying that relating different parameterizations give operators in.
There is no axiom needed for changing the parameterizations. This is a follow of consequences of the axioms. But yes, there will be something about action of the diffeomorphism group of S1 on H that follows from the axioms.
Is there any regularity on the parameterization?
I use T infinity. I suspect that it's possible to push this further to some, I mean, my understanding is that the Weil-Peterson class would be the thing that, the maximal place where you can push this. But right now, I work with C infinity. So, let me tell you a little bit what a complex cobordism is. I made this picture here, but that picture is a little bit of a schematic picture, so I can try to be more precise, and I think it's important to be more precise. What do I mean by a complex cobordism? So, I'm going to take my starting point to be a closed Riemann surface. And then, so imagine the Riemann surface that you obtain by putting disks on there and there, very much like in Eric's talk. And then I have an embedding of a disjoint union of n copies of the standard disk into that Riemann surface. And as I said, I use things that extend smoothly to the boundary. So, okay, that's what I do. And then I have an embedding of M, except that now it's going to be an anti-holomorphic embedding because from the other side, so you have n disks there, m disks there, and this thing is what you obtain by removing the images of the open disks under those embeddings. Why am I going in such detail? Because what's really important for me is to not necessarily require that these two sides are disjoint. I want the image of the open disks on the red side and the open disks on the yellow side to be disjoint, but the boundaries may touch. So for example, a thing that is allowed is I take my Riemann surface to be a sphere, and I take one hemisphere and the other hemisphere, and they touch along the whole boundary, and then my sigma here is what you obtain if you take this sphere and remove this open disk and that open disk, and sigma ends up being just one-dimensional. So that's allowed. I do keep these two parameterizations, red and yellow, and so what we end up is a one-dimensional manifold with two parameterizations. You can compose them, you get a diffeomorphism of S1. That's how you get diff S1 acting on H. Okay, so So let me sort of. Oh. Keep breaking all my chalks before the beginning. Yeah, so if you take this particular example that I talked about, so you have a sphere, my red chalk now is here, and the yellow is there. I'm going to take a disk on one side, a disk on the other side, and then sigma is the thing in between, and things that are of that form exactly, these are called annuli. And when you compose annuli, they form a semigroup, and that's called the semigroup of annuli, and it's denoted An. So this is a Siegel-Neretin semigroup of annuli, and it contains in it, I need to make some space. Let's see if I can master the art of erasing only part of the board. It's always a bit tricky. So, the group of orientation preserving diffeomorphism of S1 is the special case when the red part and the yellow part completely cover the sphere. That's allowed. And a great insight of Graham-Siegel and independently Neretin is that this should be thought of as a complexification of that. This is some kind of infinite-dimensional real Lie group, and this is a sort of infinite-dimensional complex semigroup. And this is the inclusion of a real Lie group into its complexification, if you want. Okay, so now let me tell you about this same story. When I do it for chiral CFT. So and I'm only doing unitary things. Because the techniques and tools that I use are really just things that work for unitary things. It's not that I don't care about unitary things, it's more like I have just no idea how to even formulate things in the particular way that I'm going to do it right now. So, it's again going to be the complex formalism category doesn't change, the same thing, except that it's going to land in a different target category. It's not Hilbert spaces. It's going to be so the objects of that category are going to be von Neumann algebras. I need to tell you what the morphisms are. So here, it was Hilbert spaces and bounded linear maps between Hilbert spaces. Now it's von Neumann algebras and CP maps. And I will tell you what those are. So here the objects are one-dimensional manifolds like circles, and the morphisms are these complex cobordisms. These map to Hilbert spaces, these map to bounded linear maps. Now we're going to have S1 maps to a certain algebra, one-dimensional algebra, which is the algebra of observables. Okay, now we have a name for it. And
can I ask a stupid question about the previous one still? So you said the target is bounded linear maps of Hilbert spaces, and I understand bounded you need, so you can't require trace class if you want the degenerate case as well. Did you have any requirements of trace class appearing in some case, or?
no. So, as I learned yesterday from talking to André Henriques, there actually do exist theories that I very much want to include as full CFTs, where none of the things are trace class. An example is the free massless boson in 2 dimensions. So that's a theory where this map is never trace class. There is since I'm talking about subtleties related to non-compact theories, let me use this moment to emphasize a subtlety. This definition here, doesn't fit important examples such as Liouville or the massless boson for the reason that these theories are not defined on all Riemann surfaces. What is important for these, so if I want to, the modification that's required in order for things to work is that n is strictly greater than 0 and m is also strictly greater than 0. So for some CFTs you can make it work always, but there definitely exist some examples that I don't want to disallow that are only defined when both the incoming and the outgoing boundary are non-empty. And it's related to things being not trace class. If they're a trace class, you can sort of take the trace and that produces closed surfaces. But
I think the problem you mentioned, you only need one of them to be strictly positive.
no, you need both, because if you take, for example, the cobordism that has no input and one output, which is just a half sphere, so this would produce a map from the 0th tensor power, which is just C, just the complex numbers, into H, and it would select a vacuum vector.
Okay, it would be in a bigger Hilbert space.
So and also if I want compatibility with adjoints, then requiring one condition or the other condition is an equivalent requirement. Okay, so here we have, again, the same situation. I have a cobordism. Same story as there. So n, so this is the union of n copies of S1. That's a union of m copies of S1. So the picture is exactly the same as there. And what you get there is a CP map. And I will tell you what that is in a moment. So the map, of course, depends on sigma. So let me put the sigma dependence explicitly here, going from a to the m to a to the n. So, okay, something a bit funny happens here where m and n are switched. So the map goes from n to m, and here it goes from m to n. That's not clear why I would want to do it right now, but it's not a typo. Okay, so same axioms as over there, namely continuous dependence on moduli, compatibility with composition, compatibility with disjoint unions. These are the things that are unsurprising. Here I had the compatibility with taking adjoints. I don't know what it means to take the adjoint of a CP map. I just don't know what that means. So I drop that condition. But there's one important thing that is not yet implemented in what I said, is this holomorphic dependence on the points. Right now, I didn't say anything that nothing is required to be holomorphic, so my definition is incomplete. So let me try to find a space on the board where I will. It's a tricky one, huh? I think we've seen enough of the full CFT one.
Just one question before
Yes.
breaking the shot. Can you recall what is a CP map?
Yes, I will say. It stands for completely positive map. I was planning to write it anyways, but I can say it in words while I'm doing this job talk. It stands for completely positive map. So it's a map between another algebras, which is not an algebra homomorphism, so it's a weaker condition than being an algebra homomorphism. And it's just a linear map of the underlying vector spaces that is required to send positive elements to positive elements. And so that's what it would mean to be a positive map. Now C is for a completely positive map. And a map is a CP map if it's a positive map, so it sends positive elements to positive elements, and also continues to do so after passing to matrix algebras. So I have my linear map phi from my algebra, let's call the algebras A and B. So I have a map phi from A to B. I can construct a new map from the space of n by n matrices with entries in A to the space of n by n matrices with entries in B. So I look at n by n matrices with entries in A, n by n matrices with entries in B, and if this map, that's again a von Neumann algebra, if this map sends positive elements to positive elements, then the original map from A to B is called completely positive. So maps positive elements so that's what it means to be a CP. Okay, so there's one more condition that I need after that. So plus dot dot dot, and the dot 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 continues here. So this is the one axiom that talks about holomorphicity, so let me spell it out. There exists holomorphic map from the semi-group of annuli, this guy here, to the algebra, to the set of units of the algebra, so the set of invertible elements of the algebra. Sorry, do I want it? No, not invertible at all. Just they're going to be non-zero, but the whole point is that this is not a group. Sorry, to the algebra. Modulo constants. So really what you have is a certain central extension of the semi-group annuli, and that central extension admits a map to the algebra. Here I'm just phrasing in terms of a map there, so the image is well defined up to a multiplicative constant. So we have a holomorphic map. Let's give a name to that map. Let's call it, so if sigma is my annulus, let's call the image of that thing y sub sigma. So that's an element of this von Neumann algebra. Then we want this map to be compatible with composition, so it's a homomorphism. compatible with taking adjoints. Here there's a notion of flipping in and out. Here this is a star algebra, so there's a notion of adjoint. And then the more important, and then monomorphic, and then the more important condition is such that, maybe that's here, such that phi sub sigma of A is equal to y sigma star A y sigma for all elements of the algebra. So if you restrict to analyze that happen to be diffeomorphisms, then this is just saying that these CP maps that you get, associated diffeomorphisms, that they are given by conjugation by some element, by some unitary. Now this is not conjugation because these are not invertible, and, but it's the same formula. Okay, so great. Now what I would like to do, essentially I have a choice that I have to make, which is whether I spend some time telling you why this formalism is at all related to this, namely how do I, for example, talk about this correlator in this formalism, or methods for constructing chiral CFTs in that formalism. I think I will start by giving you intuition, and then we'll see where we get. So let me tell you how we talk about this in this formalism, because right now, my guess is that this looks nothing like anything that you have seen. So, okay, so I don't need that. Okay. So what do we have? I need to tell you what are the Wilson lines and what are the local operators and all these things that... okay, so what do we have? We have a von Neumann algebra. The Wilson lines, the types of charges of Wilson lines are indexed by representations of that algebra. So in some cases where the CFT is rational, this is going to be a very simple algebra that has only fairly many types of representations. In other cases, it's a more complicated von Neumann algebra. And the local operators are going to be vectors in those representations. So the set of a local operator is going to be, so there's a version of this state operator correspondence, sometimes people call it the state field correspondence, that says that local operators correspond to a choice of representation of this von Neumann algebra A plus a vector in the representation. Okay, so we give ourselves three representations labeled I, J, K, and three vectors, phi 1, phi 2, phi 3. And okay, so what else do we need? So I told you what it means to have charge I, like has charge is just another name for is an element of the vector space. I need to tell you about fusion. So, okay, so let me tell you about fusion. So suppose I have hi and hj that are representations of my von Neumann algebra A. Then I need to define a new Hilbert space, which is the vector space underlying the fusion of I and j. So this is going to be the completion of something with respect to some inner product. And you might guess that you take the completion of hi tensor hj. In fact, you need to add also a copy of the algebra. Okay? So it's the completion of this vector space with respect to an inner product that I'm going to write down here. So my inner product, I need to take two vectors in there. So let's call them A, C, eta. Maybe A1, C1, eta 1. And then A, C, eta, index 2. So in this new so I have this inner product here, and that is defined to be maybe I go here. So I'm going to apply my CP map. I need to tell you which surface I use. I'm going to use a pair of pants. So the pair of pants, so my color scheme is that red is incoming and yellow is outgoing. So I'm going to stick to that. I have two incoming boundary components and one outgoing boundary component. And so that's my sigma that I use So let's go back to this. So this is a thing that goes from one copy of the algebra to two copies of the algebra because of this reversal. Okay, great. So now I need one element of the algebra. The element that I put is A2 star A1. And that's now an element in two copies of the algebra, and I can let it act on C1 eta 1. So it acts on this thing, and then I pair against C2 eta 2, and that inner product is taken in the representation HI, in the Hilbert space HI tensor HJ. Okay, so this is how you do fusion using CP maps. So then there's some work to do to show that this completion is a module for A, but somehow it's already built in, like I had a copy of A here in front. So if I acted an element of A on something of the form AXC eta, I just act on the A here. Yes?
A concrete example where A would be related to Virasoro, for instance?
Yes. So A, in the concrete example for A is related to Virasoro, you take diff S1, and that's a group, and you take the group algebra of diff S1. That's an abstract algebra, which is not yet a concrete algebra, and then you look at the universal von Neumann algebra of that, you do one of these standard construction in Caesar algebra and von Neumann algebra, where you sort of take a copy of each representation that exists and that you care about, and then you form a huge Hilbert space, which is a direct sum of all these, and then in that Hilbert space, you take the completion to a von Neumann algebra of this algebraic group algebra of diff S1.
Just concretely, why don't you take just the Hilbert space as before? Full CFT. In this full CFT case, you had an H, it was Hilbert, or...
Yes.
And why here no Hilbert space?
Well, the Hilbert spaces correspond to the Wilson lines. And
The Hilbert space is more related to the H-gen, or the space where you have representation.
sorry, again.
Which you can do whatever you want for this. I agree, but then there is a gap between what you used for full CFT and for chiral. And we were just.
Well, there's different things.
Yes, but why? What motivates differences in Hilbert and the fundamental?
So when you have a quantum field theory, the expectation is that you have a Hilbert space whenever you take a Cauchy slice of some space-time manifold. So if I have a quantum field theory that lives on two-dimensional surfaces, and I take a Cauchy slice, what I see is something one-dimensional. And so there is a Hilbert space associated to one-dimensional thing, one-dimensional manifolds. There are not so many of them, they're all just circles. So you just need to have one circle, you get one Hilbert space. Chiral CFT is a thing that lives on the boundary of a three-manifold. So if I take a Cauchy slice of that, what I get is two-dimensional manifolds with one-dimensional boundary. These are the things that have associated Hilbert spaces. You can say, okay, well, I'm going to care only about the case when my two-dimensional manifold is a disk with a boundary. Well, you can do that, but then you're missing part of the information. You've sort of like decided in an ad hoc way to restrict the topology, whereas I want to have the full information. Okay, great. So we have all these circles with a piece of topological two-manifold inside that might have some genus. Okay, and then you can ask, what does a theory associate just to the boundary without the knowledge of what thing I have on the inside? So what's in common between the chiral CFT will have a Hilbert space corresponding to that, a Hilbert space corresponding to that where I have a bit of genus, a Hilbert space corresponding to that where I have two of those. And then you can ask what's in common between all these Hilbert spaces that only depends on the boundary. And what's in common is that all these guys are representations of an algebra, which is the same algebra that lives now on something one-dimensional. And so, in fact, that algebra is a thing that contains all the information that you need. So somehow you don't need to carry all these Hilbert spaces. You can think of them as being things that one reconstructs from this setup. But what I was doing right now is trying to explain how one assigns a number to this situation given three representations, I, J, K, of the von Neumann algebra, three vectors, phi1, phi2, phi3, living respectively in Hi, Hj, and the complex conjugate of Hk. And now I have here, I told you what this fusion is, so a morphism of representations of A from this fusion to K. Okay. So that one up there I don't need.
I have a question.
Yes.
So here on the bottom,
this sigma belong to the annulus.
Yes.
But on the top, you define this phi associated some pair of pants.
Yes. So this is the one axiom that these guys are required to satisfy that is not analogous to the axioms that exist in full CFT. This is like, so I sort of said out loud without writing the axioms: compatibility with composition, compatibility with disjoint union, a continuity condition. These are the things that I don't want to write them down because they're the obvious things. And there's one non-obvious axiom which is written here. And this non-obvious axiom is an axiom that is only for annuli. No, it's an axiom that is only talking about annuli.
So this map of phi, capital phi can also be associated with any surface.
That's part of the data there.
Okay.
So the data there says I have one von Neumann algebra that I think of as corresponding to the circle, and for every complex cobordism, we have one of these guys. Yes.
I think I'm still a little puzzled about the definition of diffusion, especially with respect to what you complete. So first of all, did those boundaries of the pair of pants need parameterizations? And did you say something about those? And second of all, I don't know if the second question is fair, but can you provide an intuitive way of thinking about what just went into this choice of the with respect to which you complete?
So there is a perfectly valid objection, which is I need to specify like a very concrete choice of pairs of pants. I need to tell you which complex structure I use and how I parameterize in order for this to be well defined. So I choose the pair of pants that starts at the point -6 and goes to the point +6, and those intermediate points are the points -4, -2, +2, and the circles are round. And okay, now I've made a definition. Now I can object, well, what if I chose -7 and +7? It is a consequence of this that the result is independent of how you do things. Because any pair of pants, you can go from one to the other by gluing in annuli, and anyways, there's work to be done. I'm happy to go over that, but once that work is done, then this becomes a well-defined operation that's independent of these choices. Okay, so let's finish this job of defining what this is. So how does that work? So let's recall what we have. We have phi1 in HI, phi2 in HJ, phi3 in the complex conjugate of HK, and then the correlator is going to be given by an inner product taken in HK. Here I take phi3 bar. Phi3 bar is just the same vector as phi3 except viewed in the Hilbert space HK. Whatever. It's the same thing as phi3. And then I do f of, well, so I have phi1 and phi2, and I can use phi1 and phi2 to construct a vector in the fusion, namely, so I'll just write it like that. I'll write phi1 fusion phi2, and then I'll explain what that means. That's the image of one tensor phi 1, tensor phi 2 in HI fuse J. Right? I mean, I said that this fusion is a completion of A tensor HI tensor HJ. So if I take a vector in HI and in vector HJ, I can make in an obvious way a vector in there. I use this notation. Now that's a thing to which I can apply F, because F was, oh, I didn't say what F is. F is a map from HI fuse J to HK. So I apply it, now I'm in HK, and I can take this thing, and I've arranged the complex conjugates so that this is complex linear in phi 1, phi 2, phi 3. So this is an illustration of how this formalism up there recovers things that might be familiar. Of course, you can ask, how does it recover more things like higher genus stuff? Oh, okay, you can try to do it. I claim that this is a thing that this formalism is well adapted to doing. So I was, if I had extra time, I would have told you a little bit about methods for constructing examples of these things. Sadly, my time is up, so I will stop here.